Greetings, dear friends. Thank you for keeping on TV Math Hub. For those who haven't subscribed, please do so such that you can get the series of the videos that we'll be following for all our lectures. Dear friends, last time we had started on what we call the partial differential equations, whereby we looked at the definitions of the partial differential equation, the order, and what we call the degree of the partial differential equation. We as well looked at how best you can get the degree and what we call the order of the partial given a partial differential equation. Today in this lecture we shall look at how best we can form a partial differential equation when we are given an equation that is containing arbitrary constants. However, before we come to the formation of the partial differential equation, I will first of all take you through in some of the terms that we shall also be using during this part of the partial differential equation. For convenience purposes, dear friends, we shall have to use some of the short forms. For example, if, for example, we find that we have del u del x, someone can represent this as u of x. The short form of this one here, we shall always be using u of script x. If someone says del u del y and simply represent this as u of y, this and this within the partial differential equations will be meaning the same. And the terms that will be commonly used here are what we call del z del x. Whenever we have del z del x, instead of using del z del x, sometimes we shall be using p. Del z del y, most times we shall be using del z del y as q, then del 2z del x squared as r, del 2z del y squared as t, and del 2z del x del y will be representing s. So you need to get these terms here. We shall always be referring to them when we are forming a partial differential equation. At times, someone might leave his or her answer in terms of del z del x, or someone can put the answer in terms of p, in terms of q, r, t, and s. In other words, you need to be knowing what does q represent, what does p represent. Del z del x will be standing for p, del z del y will be standing for q, del 2z del x squared will be standing for r, and t will be standing for del 2z del y squared, and s will be standing for del 2z del x del y. Now, having looked at that, let us briefly look at how best we can form a partial differential equation given what we call an equation that is containing arbitrary constants. So looking at how we shall be forming an equation or a partial differential equation, we shall first of all look at, suppose you are given a function that is containing x, y, z, then two arbitrary constants, that is a and b, and that given equation is equal to 0. So when you have such an equation, that is f of x, y, z, a, b equaling to 0. Our equation is containing x, y, and z, then plus two arbitrary constants, a and b. Now, these two arbitrary constants, a and b, we need to eliminate them. But as you know, if you have two arbitrary constants, then you need two equations that will eliminate these two constants. Now, how do we form equations that will help us eliminate the arbitrary constants a and b? Now we need to take into consideration that for our given function f, which is into x, or an equation which is containing x, y, z, a and b, we need to note that this z here is a function of x and y. If z is a function of x and y, so it means we can get the partial derivatives of z with respect to x, the partial derivatives of z with respect to y in each of the equations. Now, how do we get that? We shall first of all look at this equation, that is f of x, y, z, a, and b, which is equal to 0. This equation here, when we differentiate it with respect to x, so get the partial derivative of this function with respect to x. But because this z is also in terms of x and y, then we shall also get z with respect to what? With respect to x as well. So differentiating also the function, that is the f the z, that is, we are differentiating the function f, this function here, with respect to z. But also remember that z is also a function of x and y. So it means here, if we get del f del z, since we need del f del x, then here we shall multiply by del z and del what? Del x. And this equation will be equal to 0. So we are doing that because you have, if you form a tree diagram here, you have f. F is in terms of z, f is containing z, x, y, a, and b. So this f here is containing z, but remember z is containing x and y. So you have f, you have z, you have x and y. So when we take the partial derivative of f with respect to x, then to add there del f, del z, then we must also consider the fact that z is also an dependent variable which is depending on x and y, and for this case y will be a constant, a and b will also be a constant because we are taking the derivative with respect to x. So that's why we shall have such an equation. Similarly, we shall do the same for y, and we shall be able to come up with this equation here. So we have these two equations, equation 1 and equation 2. So having these two equations, we shall solve them simultaneously, or you look at how best you can solve the two equations such that you are able to get what we call, you are able to eliminate a and b. Our major purpose is to eliminate a and b. So look at how best you can use these two equations to eliminate a and b. So that is basically what we shall be doing throughout. So dear colleagues, let us come to our examples here. We want to form what we call a partial differential equation when we are given the equation z, which is equal to x minus a squared plus y minus b squared. How best can we form a partial differential equation from this given equation here? Our major purpose is to eliminate a and b. Our major purpose is to eliminate a and b. How best can we eliminate that? Let us do so. Let us take the derivative of z with respect to x, since z is in terms of x and y, then plus our arbitrary constants a and b. So when we take the derivative of z with respect to x, will give us, differentiate this, we shall have drop the 2 into differentiate x minus a. X minus a differentiated will be 1 into x minus a to power 2 minus 1. But this will be same as 2 into x minus a. 2 minus 1 is 1. So we have delta z del x, del z del x as equation number 1. Let us do the same for y. So we have eliminated this part here, we have not considered it because we are differentiating z mainly with respect to x, and we realize that here we don't have x, so this part here will be 0. That's why it is not considered here. Now let us differentiate now with respect to y. So del z del y will give us, this part here will be 0 since it is not containing y. Now let us come to this part. We differentiate the same way we have differentiated up there. It will be 2 into y minus b. and this one will give us equation number 2. When looking at equations 1 and 2, we are looking at how best we can eliminate a and b. So how best can you eliminate a and b given these two equations here? I realize this is x minus a, this is y minus b. But when I come to the equation here, which equation maybe, let me call it equation star, I realize I have x minus a, y minus b. Let me make x minus a the subject here, y minus b the subject in equation 2. I come and substitute them in equation star. Let us try out that. So we are saying from equations 1 and 2, from equations 1 and 2, from equation 1, from 1, I will say x minus a is same as a half delta z del x. So from equation 2, from 2, I can say I'm making y minus b the subject. So y minus b will be same as a half del z del y. So I have y minus b, I have x minus a. What you do? Substitute x minus a, y minus b into equation star. Now equation star will be, equation star becomes z, which is equal to x minus a. X minus a is a half del z del x. But x minus a is squared, so we shall have this squared plus y minus b is same as a half del z del y. So it means this will also be squared. So we shall have z, which is equal to a half squared will give us a quarter del z del x, where the whole of this is squared, plus a quarter del z del y, where the whole of this is squared. So someone can multiply through by 4 to get 4z, which is equal to del z del x. Del z del x, the whole of this, which is squared, plus del z del y, the whole of this when it is squared. And this will be a partial differential equation that is not containing a and b. Similarly, someone can represent this one in terms of PQ, as we had seen earlier on how we can conveniently represent del z del x and del z del y. So using the same technique, where we have del z del x, we shall put p, del z del y, we shall put q. So we can represent this as 4z, which is equal to p squared plus q squared. So this and this are two equivalent equations, and that will be the partial differential equation we shall form for part 1. So that would be part 1. So we shall look at. So I hope we are moving on well. Let us look at example number 2. So example number 2 says that x minus a into y minus b minus z squared is equal to x squared plus y squared. We want to look at how best we can form a partial differential equation given that equation there. So friends, what we shall do is not different from what we have exactly done in part 1. So let us do the same here. We shall get the partial derivative of z with respect to x and partial derivative of z with respect to y. So let us look at the partial derivative with respect to x. Now with respect to x, we want to differentiate this expression here in respect to x. Now what we shall do, when you are differentiating with respect to x, you have to put into the mind that y will be constant. Now, for that case, if I'm differentiating this one here with respect to x, I will treat y minus b as a constant. Then when I differentiate x minus a, I will remain with 1, because when you differentiate x, you get 1. So let us have 1 into y minus b minus, I'm differentiating z squared, so differentiate z squared normally, get 2z, but because you are differentiating z with respect to x, so you will put del z del x, and this one will be equal to differentiate x squared and get 2x. When differentiate y squared, you will get 0. So this will be plus 0. So we shall have y minus b minus 2z. Friends, we said that if we have del z del x, for the purposes of convenience, we can use p to represent del z del x. That is what we began with when we were introducing this lecture. So this one will be equal to x. Let us, because when you look at this, you realize that your main interest is to eliminate b and a. So if I have y minus b, and here I also have my y minus b, I can easily make y minus b the subject, such that I have y minus b, which is equal to 2x plus 2z p. So I can call this one here equation number 1. Now let us go on and get this expression here. I will differentiate that expression with respect to y. Now when we differentiate with respect to y, what shall we have? We shall treat x minus a as a constant because we are differentiating with respect to y. Then x will be considered as a constant. In other words, when I differentiate this expression here, x minus a into y minus b, I treat x minus a as a constant. So I will have x minus a times, when I differentiate y minus b, I will simply get 1. So I have times 1 minus differentiate z squared. Normally get 2z, but because I'm differentiating z with respect to y, I will put del z del y. And this one will be equal to x squared is a constant, so it will give us 0. Y squared differentiated will give us 2y. So for that case, if you remember what we said, that del z del y will always be represented using q. So we can say this is 2z q, which is equal to 2y. So since when I in this equation here I have x minus a, and my interest is to eliminate this a here, so I can make x minus a the subject, and I have x minus a, which is equal to 2y plus 2z of q, and we can relate this one here to be equation 2. So what are we getting here? You realize from 1 and 2, I have y minus b, I have x minus a. So using y minus b and x minus a, I can eliminate a and b from the general or the given equation by substituting for 1 and 2 into this equation. So let me let this equation to be equation star. Now substitute 1 and 2 into equation star. So what? So we are substituting equation 1 and equation 2 into equation star, and from equation 2 we are having x minus a as this, and from equation 1 we have y minus b as this. So let us substitute y minus b and x minus a into equation star. Now doing so, we shall have 2y plus 2zq into y minus b is 2x plus 2zp. We are subtracting z squared, and this one should give us x squared plus y squared. So we can try to simplify this. This is same as 2 outside. This is also 2, so it will give us 4. So that is 4 into y plus zq into x plus zp minus z squared, which is equal to x squared plus y squared. Now, if you reach here, you can take z squared the other side, and we have 4 into y plus zq into x plus zp, which is equal to x squared plus y squared plus z squared. So you can simplify further this, or you can leave your answer at that given state. because we already have the partial derivatives, that is 2p, then our equation does not contain a and b. So this will be our answer for that example number 2. So I hope that one has been clear. When you look at the steps we have done, someone still at this point where we introduce p, someone can maintain del z del x. You can maintain del z del y, but you realize using p and q can simplify life, as we can say. So that is our example number 2, and we shall move very fast and look at example number 3. At example number 3, we are having z in terms of x, y, and t, and we want to eliminate the constants, the arbitrary constants, a, b, and c. So how best can we do that? We shall not differ from what we have been doing. We shall look at the derivatives of z with respect to x, y, and t. So taking the derivative of z with respect to x, we shall have del z del x, as when we differentiate this, it means y will be considered constant, t will be considered constant. So this and this will cancel out. We shall remain with z, we shall remain with a. So that will be equation number 1. 2, we shall take the derivative of z with respect to y, and this will be x is constant, t is constant. So we shall remain with b, because we are having by. When we differentiate that, it will be b. So similarly, del z, del t will also be c, taking x and y to be constants. So we shall have this equation 2, this equation number 3. Now from the given equation, which we can name equation star, we can substitute equation 1, 2, and equation number 3. So we shall have z as a is del z del x. So we shall have x del z del x plus b is del z del y. So that is del z del y. We are multiplying this by y, then plus c is del z del t. We are multiplying this by t. So this will give us x del z del x plus y del z. It is y del z del y plus t del z del t. And this will be our partial differential equation that is not containing a, b, and c. So lastly, we come to example number 4. So hoping that the methods are now clearer, we shall move a bit faster here. So we have z as ax plus by plus cxy. Using the similar method of getting del z del x and del z del y, we shall get del z del x first. Now, when I have z as ax plus by plus cxy, when I differentiate with respect to x, y will be treated as a constant. So I will have del z del x, which is equal to, when I differentiate this, it will give me a, then by will go to 0, then cxy differentiated, since c and y are constants, so I'm differentiating with respect to x. So I will remain with cy, and that will give us equation number 1. Looking at now the derivative of z with respect to y, I will take x as a constant, so ax will go to 0. When I differentiate with respect to y, by will give me b. With respect to y here, cxy, so cx is a constant, but I have y here, so when I differentiate this, I will remain with cx. So I will have this as cx, and this will give me equation number 2. So, dear colleagues, when you look at equations 1 and 2, you realize it might not be easy to remove the constants a, b, and c. Now, what do we do? You realize in our equation here we have ax, here we have by. So, if I want to eliminate these constants here, I look at how best I can relate these equations here with my equation that is given. That is basically what we have been doing in the previous examples. So if I want to relate this and the equations I'm having, if I have a here and this is ax, then I think of multiplying by x in equation 1. If I have b here and this is by, let me think about multiplying y here, such that I can easily create the relationship between the given equation with the equations I have formed. So doing so, let us multiply equation 1 with x. So from 1, I can say that x del z del x can be same as ax plus cyx. From 2, similarly, I can say y del z, y del z del y is same as by, by plus 2 is plus c xy plus c xy. So that is what we are having there. That is what we are having there. So I will have this as c xy. Now I can call this one here as equation 3, and I called this one here as equation number 4. Now we realize that from equation 3 and 4 we can have some relationship there. Now let me add adding equation 3 with 4. When I add equation 3 with 4, what do we get? When you add 3 and 4, you will have x del z del x plus I'm adding this one here with the corresponding term, which is y del z del y, and this one here will give us, this is ax, I can add it together with this, that is ax plus by plus, when I add cyx with cyx, then I will create 2cyx. Why are we adding, not subtracting? Because when you look at this is cyx and cyx. Someone would think of subtracting first. But remember, in your equation here, you have a plus. So it would be better to add than subtracting. So that's why we are considering the addition instead of subtraction. So someone would easily see or look at how best to eliminate cxy. But focus at this equation here with the given equation. Now looking at this, can we realize that ax by, here we have ax and by. So there is some relationship between this equation here and the given equation. So we are saying from equation star and equation 6, x del z del x plus y del z del y will give us z. Here we have z plus c is del 2z del x del y, then times yx. So we have this one here times yx. So you can rearrange it well, and that will be your partial differential equation after we have eliminated a, b, and c. I hope the methods are now clearer to each one of us. I cannot go minus giving you some numbers to try. So let me give you one number that you will try out, and that is where we shall stop for today. I will thank you so much for watching.